I'm sorry because yesterday I kind of changed the order. So I didn't speak about infinite interacting particle systems. That's the goal of today's talk. I figured it would be nicer if I gave an overall picture, discuss the techniques and the main ideas. So I prepared that as a sort of introduction. And today I'm in a way building on most of the ideas we developed yesterday, but they are more like illustrations in research type uh, contexts. So what I'm going to tell you today is a particular result that comes and follows from my research on this topic of interacting particle systems. That is a discussion about limits of reaction diffusion models on infinite graphs. Right. So the plan of the talk is to explain the result. So that's what I want to do. So before I can state, I want to say a few words about where the question is coming from. And afterwards, I'll show you a scheme of the proof. So the first part of this talk is mainly setting the stage for making sense of what is the question that we're looking at. Afterwards, we could have divided the talk in two, but I think it's worthwhile, and I am more and more interested in the challenges of constructing interacting particle systems that are not necessarily finite state spaces or that have instantaneous configurations. So the construction builds from the finite state construction. So this is the finite initial conditions. IC here stands for initial conditions. Then we move further to compact spaces, which are not necessarily finite. For instance, the interval 0, 1 is compact, but it's not finite. Right. And then we complete the construction following a hint from Liggett and Spitzer. It's the Liggett-Spitzer, I call it the Liggett-Spitzer extension. Right. I don't know if they would be would agree, because there are some things that are not exactly in their spirit, but we'll see that. Then after we have constructed these particle systems, these Markov chains, we are ready to consider their scaling limits. There is a family of interacting particle systems, and then we go back to what we spoke yesterday, how to extract the convergence subsequence and characterize the limit. So it would be a standard application of the Martingale methods, the Martingale problems, if it were not the case that the limit points are not a priori unique. So we need to find a way out of the well-posed. The Martingale problem is not well posed. So we need to find another way of explaining and proving convergence. And that's the idea of today's talk, this first one. Right. Again, if you have any questions, I'm really happy to take any questions at any time. And please go ahead, come forward. For now, I want to say that, oh, sorry. Oh, again. So for now, I want to say that this is the growth of my research that I started during my PhD under the supervision of Milton at IMPA. Milton Hara was my supervisor in IMPA. And the basic point is to explain from a probabilistic point of view the evolution of reaction diffusion systems. Actually, after the defense, there was a question that was asked. The basic question was, what happens on infinite graphs? So I've taken this question to heart, started studying it and looked for some help. And these are my collaborators, Conrado da Costa from the Federal University of Rio de Janeiro in Brazil, and Daniel Valezin from the Groningen University in the Netherlands. So as you may guess, I finished my PhD in 2016, and it's been 4 years ever since. So I have many institutes I have to be thankful for many institutes for supporting this research. So in particular, I was at IMPA when I started it. So IMPA in Rio de Janeiro, the Federal University of Rio de Janeiro, both Leiden and Groningen University in the Netherlands, and finally Durham University, where I found the space to complete, but it was slowly developing throughout. So I'm very happy to show you the result of this research. So let me explain the question to you. Basically, an interacting particle system is a probabilistic model that emulates, or in some sense captures with realism, the physical properties of a certain physical phenomenon. So here I'm showing you the reaction from ozone and oxygen. It's a reversible reaction that happens in the atmosphere. So the point is that several of these chemical models or biological models, in our case here, chemical model, they have nonlinear interaction rates. So basically, because a reaction depends on a successful collision between multiple particles, and this gives rise to nonlinearities. Right. Basically, what we're going to the perspective that we have here is that we are looking at space as divided into reaction cells, and these will be the sites where we will allow a large number of particles to interact. And so what we have here is models that describe with a certain degree of precision the changes in the particle quantities on each site, right? So this is very general, but for concreteness here, we're looking at this oxygen ozone model, right? The question was originally stated on a finite graph, but then at the end of my exposition in 2016, the question was, what if your ozone lives in a very large space, say the atmosphere, and we don't want to model with a finite number of sites, but an infinite number of sites. So what happens in the infinite case? So as you may guess, this is a rather abstract question, but it really is probing how stable our construction and our analysis is to, let's say, this large limits when we take our box, our bounding region to infinity. So that's the motivation for the questions that we're asking here. Basically, you may recall the idea is that these interacting particle systems, when properly scaled, can give rise to solutions of stochastic differential equations. And these stochastic differential equations are diffusions or motions that are continuous, and the particle systems, they are discrete. So typically we have to consider some sort of scaling to make sense of our coarse perception of the reality, because when we look at the microscope, we see the transitions are not smooth, right? The basic mathematical connection between these two objects is the notion of Martingale problems. So you remember the particle systems give rise to a family of thinking martingales that then we can represent as, after scaling, as the integral with respect to the Brownian motion, which is this universal representation of noise, of continuous noise. And then we have a solution to the stochastic differential equation. But for now, let me go back to the original investigation. Let's say we're tracking a certain chemical reactant in a region, and we're trying to say something about its evolution. So the classical reaction diffusion partial differential equation tells us that as time goes by, so U here is keeping track of the density in space and time of the reactant, here the oxygen if you want, and this diffusion here we expect converges to a certain equilibrium. So at equilibrium, this derivative in time is not present anymore. So we may as well replace this for 0. And the question then becomes, when is it, what type of functions satisfy this equation? What type of profiles, density profiles, satisfy this equation? Still a very multidimensional question, is in functional space. But if we allow ourselves to think that the equilibrium is spatially homogeneous, so that we won't have to deal with the Laplacian, because there's no diffusion, we eventually reached equilibrium across space, then we have reduced the problem to a simpler, very simpler one. We're just looking at the roots of some function that we assume is very smooth, analytic, right? And so that's basically what we're looking at. And once we have reduced the problem to a one-dimensional question, now we're looking at the roots, looking at the stable points of the roots of a certain function f. We can attempt to model the evolution of the process using a single birth and death chain. And the idea is that we are capturing the motion of the mass, the fluctuation of the mass, with different levels of precision. So it's as if we were filming or weighing with several different instruments the same phenomenon. So there is a macroscopic phenomenon out there. We are looking at it with different instruments with different precisions. Each instrument will measure different type of transitions. The more fine can measure a lot of transitions. They happen in a faster scale and they are of a smaller magnitude. The coarser the instrument, the slowest the rate, and the bigger the jump. So the idea is that as we allow the precision to go to infinity, we want to recover the true motion of our object, which should be something continuous. So that's how these fluid limits give rise to solutions of these law of large numbers for these differential equations, right? So basically, after we have modeled these processes, these are deterministic equations. The law of large numbers really shows that the noise is vanishing at that scale. But after we have examined the law of large numbers, the idea is to zoom in and to observe what is the behavior of the noise. So what we're doing here is that we are looking at the stable point. Here is referred as 0. It could be somewhere else. So it could well be, let me make a attempt to make a drawing here. So it could be this point here. So as we try to go away from this point, the system wants to restore the concentration. So this is a stable point of our function. The idea is that if we zoom in, what type of excursion do we observe in the total mass? That's after we had simplified the problem from functional space from a partial differential equation to a one-dimensional problem. So we can characterize these excursions, these fluctuations, and the scales at which they occur. But a more challenging question is, can we make sense of the spatial interactions of these fluctuations? So if in some site we have more particles, they are likely to move across from one region to another before they are restored to equilibrium. So what we're looking at is the spatial description of all these fluctuations. So divided in a grid. So we are not refining space infinitely, but we are having these reaction cells and we're following the fluctuations that happen there. So what we're basically allowing as a probabilistic model is we're allowing for transitions that are of jump particles going from one side to another. We're allowing for birth of particles and annihilation of particles. So creation, annihilation, and jumps. These are the basic transitions that we look at. On a finite graph, let's say this is established. But the question was then, can we say something about the infinite graph? Can we allow these models to be on an infinite graph? What can we say about the fluid limits then? So the classical way to construct processes in infinite lattices is to examine what is happening inside a box. So this is a small box around the origin. So you can see here, I'm going to illustrate. Like my drawing was so beautiful, now it's not anymore. But you see, this is a box around the origin, and we want to know whether the particles that are the dynamics that happens outside from very far away, outside of this box, will they influence the value of the R dynamics inside this neighborhood of the origin. So what we're trying to see is how stable is our process as we allow the boxes to expand. Right. So now that I have explained you where the question is coming from, I can tell you the result. So the result is that we're dealing with a countable infinite set. Typically, we can think like in the setup that Hugo was saying, Z. We can think of that. So on the countable set, we have a probability transition kernel P, which modulates the way particles jump from one place to another. And we also have parameters K and L, which stand for the nonlinear rates of reaction. So after that, we can assemble these stochastic reaction diffusion equations. The name comes from the fact that this is the stochastic part, stochastic reaction and diffusion. Stochastic reaction diffusion equation. Right. So that's the type of equations that we're interested in looking. Basically, that comes from the fact that these were the fluctuations we observed for a single site, and we hope somehow that this is also happening in the multidimensional setting. So these is the class of equations that we are studying. The discrete Laplacian is dependent on the probability kernel, so it captures the geometry of our space. What we're doing here is that we are seeing the net flow of mass across the graph. And this is driven by the rate at which particles jump from one place to another. So here I've written y is a neighbor of x. Just is because if they are neighbors whenever the probability of jumping from y to x is positive, or the probability of jumping from x to y is positive. So this is, we could have dropped the symbol here, just written the sum over all y and x in the graph, in the set of vertices. Right. The result is the following. These equations, these reaction diffusion models, this approximation scheme, they still are valid in the sense that we can solve these equations as the limit of those interacting particle systems. Right. So the idea of the proof is that we started with a certain stochastic differential equation that we want to model. From there, we are going to choose a family of generators. They are in quote marks because they are formal generators. They are not exactly the type of objects for which we can construct an exponential and construct the semigroup with an exponential operation. So it's not the standard context where we can talk about generators. But well, they capture the local rates, the local reaction rates that we have in our system. So from the stochastic differential equation, we build, and there's a way of seeing how we're going to build. We build these generators. We assemble the particle systems in a way, and now we have a family of processes that we're going to study, and we're interested to study the limit. So our goal here is to understand how the processes psi-n or zeta-n converge to a limit process, and that's basically going to be dealt with with the tool of thinking martingales that help us understand tightness for our process, and to say something about the limit martingales if they solve a martingale problem. So when we have a solution to a martingale problem, we know what is that this can be represented as a solution of a stochastic differential equation. But in our case, this is an infinite stochastic differential equation. We don't have uniqueness of solutions here. So we need to find another way. So we cannot follow this part of the scheme actually breaks down. We cannot use the uniqueness of the solutions of SDEs to say that we have a unique limit point. So our first challenge of today is to talk about the construction. That is to make sense of this quote marks here in our generators, build the particle systems. Then I'm going to say a few words about how we obtain tightness and how we use our martingale problems in combination with the estimates we had from the construction step to prove convergence of the entire family. So this is the plan. Right, now we are starting the construction. If you recall, there was this idea of constructing particle system by following exponential clocks. The first marks that appear, that's the transition you make. The type of transitions we have here are birth, creation, annihilation, and jump, right? So this is birth of a particle, that's the death of a particle, and this is a jump. So x plus, this is, let me just say here, this is the birth and death chain. And this is the jump. The jump couples the dynamics. So if there were no jumps, these processes would evolve independently, and we might study just a single coordinate, and it would be a one-dimensional problem. Right. The point is that we're going to have some transition rates for these operators to occur, and these rates are not entirely specified here. I'm just writing F plus and F minus for the reaction rates. The jump rate, you can read here this Pxy times eta x. It's telling us that particles are jumping independently. So they jump independently. If you have eta x particles, the rate is multiplied by the number of particles. And they follow this transition kernel P, which may allow for long jumps, but if you, for concreteness sake, we can think of this just as a finite range transition kernel. Right, the reaction functions, they need to satisfy some hypotheses here. First is that the annihilation dominates the creation of particles, and this reflects that we are in a stable scenario. That is, if we deviate from it, there is this restoring force that is moving us back to the origin or to the equilibrium point. The other thing that is important is that once we reach zero, we kill the process. It stops there. There's nothing else is happening. So we're looking at a single excursion. And also, the final hypothesis is that the difference, this is the net change of mass in our system, essentially, that this is a decreasing function, in the sense that the further you get away from this equilibrium point, the stronger is the pull. So that's not just a physical hypothesis, a mathematical one, because it helps us to prove that the system is overall attractive. It's reducing the distance between different configurations, and we're going to rely on that as we make our coupling estimates, which is the key of our construction. So our goal is to construct a dynamics that jumps according to these basic marks. So I'm taking A, one possible mark can be a birth, a death, or a jump. And I want to see one of these transitions with the specified rate. So that's our dynamics. And it's not clear that we can construct these processes. So just to recall, this is a quote from Liddle. In general, there are infinitely many particles in the system, and infinitely many of them make a transition in any interval of time. So the transition rates for individual particles depend on the entire configuration. So it's not immediately clear whether the specification of the local dynamics determines the evolution of the system as a whole in a unique way. So before proceeding to analyze the infinite system, it's necessary to examine the question of existence and uniqueness. So that's where we stopped. We stopped for a long time the question of what happens in the infinite graph. We were trying to make sense of the process. So the starting point is one that is amenable to the intuitive construction that we have, which is, can we say something about the first transition that occurs? Can we evolve the time forward using with some holding time? Can we make sense of our state space or of our chain of events? So the first point that we start from is the finite configurations, those that have only a finite number of particles. So they are allowed to live in the entire graph. The transitions are not restricted. If you go away from the box, you are, let's say, eliminated. There is no boundary condition of this of sorts. But we do restrict the initial configurations, and that makes us live in a countable set of possible states that we're visiting. Right. The next extension, which is not a straightforward extension, is to consider the space of uniformly bounded configurations. So, okay, we cannot say what's happening for every configuration, but we can say what's happening to all configurations that are uniformly bounded. So pick M like a very large number, say a billion, I don't know, a very large number, and you should feel confident that if you can make sense of this evolution, you have already expanded very much the type of processes that you're analyzing. So as we'll see, that's not the whole story. We can go beyond that. We can find a space E alpha that contains both E0, the finite configurations, and the uniformly bounded ones. And this will be, this is what we call the Liggett-Spitzer extension. And I'll say a few more words on that. But for now, that's how we start. So let's start our construction from the finite state spaces. So the basic idea is that we're going to couple all the evolutions according to a family of Poisson point processes associated to each mark. So whenever one of these clocks, say that these underlying clocks behind the Poisson point processes, whenever we see a mark or we see one of these clocks rings, this will indicate how we are transitioning. So I want to describe this in detail because it's a crucial coupling that will allow us to do so many, allow us to make the extensions we're looking for. So our probability space is just the collection of all these Poisson point processes, and we're taking the same marks for all initial configurations. So what we're creating here is a random flow that is mapping and saying what's happening to all configurations eta over the interval of time S and T. So this idea of random flow, I think we took from Jan Swart. So his lecture notes on interacting particle systems. Maybe very classical, but that's what we looked at. Right. So the starting point is a time zero, or when if we don't move anything, we stay fixed. So we start from S and eta, and if we have a positive time, we can build a sequence of events. We can build a chain of events just by looking at what is the first time that we see a mark that is allowed. So this may look cryptic in the beginning, but the Poisson point processes are in the positive quadrant. They have rate 1. This is a Lebesgue measure Poisson point processes. And we have a threshold here, which is for every mark A, we have Ra of eta. This is eta k minus 1, which is the configuration we're sitting in. We're trying to see where we're jumping to. So we have a threshold here, and we're only incorporating the marks that happen below. So you can see that the rate at which a mark appears is exactly Ra eta. That's the reason why we coupled in this way, because we can change the configurations and still use the same family of marks. So if we have a mark over here, we will not consider that as a valid point. This is the time here, S. So if a mark occurs below the threshold, this is a valid point. So the first one for each mark, so we're going to consult all the marks. The first one is the one that we are going to perform. Okay? So this gives us an almost sure definition of what is the transition. Here I have written, take all possible elements that have satisfied that for the specific infimum time. But that's in general a singleton with probability 1. Sorry. And because the rate of our because our configuration is finite, the sum of the rates is also finite. And this tells us that also that almost surely we are moving forward in time. If you had infinitely many particles making transitions, if you had an infinite rate, we will not be able to find what is the first transition that happens. We will not be able to construct the chain of events. So we are heavily using the fact that this is a finite configuration. So while this sequence of times are less than t, we can continue building our chain. There will come a point. There will come a point where we will not find an sk less than t. In that case, we're looking at the infimum of the empty set, which is by convention infinity, and that will tell us when to stop. We'll find this depends on our Poisson processes omega, but there is a finite number of transitions that we'll perform, and afterwards we stop. We set our flow of our configuration eta across time s and t to be this final state here, eta to the power k star. This k star is this special, is the kth configuration that we have built using this rule here, updating according to the first mark that appears. Right. That's the construction in the finite space. In the compact space, what we are doing is we're doing two things. One is we can consider the finite configurations and build an m truncated version of our flow by simply prohibiting particles to go beyond the value m. We cancel the addition of particles if we would go above m. So that's what this is doing. This is a truncation of our transitions. We don't need to truncate the removal of particles because they are only helping us approximate the different configurations. So that's this flow here defines the flow in a subset of EM. So it's not the whole EM. So it doesn't define the dynamics for all possible configurations. To do so, we're following the classical construction using Healy-Yoshida approximation that's done in chapter 1 from Liggett, which makes sense of these formal generators as true generators of a semi-group that eventually creates our process. Remember that we read this as saying from eta, we jump to this new configuration, which is, let's say, gamma AM eta with rate RA. So that's how we read the generator to build our clocks. But in fact, we can go beyond finite configurations and really extend that to any point in our compact space. What is interesting is that if we look at the flow, the truncation is clearly a monotone function. If we are annihilating a particle that would appear and we annihilate it at different levels, at a higher level, if we let m increase, the configuration of particles that we are creating is also increasing. So an also important thing that we see here is that we were canceling the excursion when we restored the total mass to 0. So if we eventually reach 0, we stay there. And that makes the case that since the number of deaths is stronger, the rate of death is stronger than the rate of birth, this makes it that eventually all the particles will reach 0. So let's say we're looking at finite configuration, the total mass here will eventually, it's symmetric, it's dominated by a symmetric random walk that will eventually reach 0, right? And so this tells us there is a maximum value that may depend and will depend on the type of transitions that we're looking here. If there have been many creations, it can go higher. It really depends on the omega. Right, this is a random thing. Eventually gets to 0. But there is a maximum value there. And afterwards, the construction of our truncation is no longer active, so we can be happy with our flow. Very good, but it's not entirely satisfying yet, because every configuration will be perturbed. A particular configuration eventually gets undisturbed by the truncation as we let the truncation go to infinity. But every point in our construction will eventually face this truncation, and that's a little artificial. So to go beyond that, to go to a space where we allow for more configurations, we consider the space E alpha, which is based on the alpha norm. Then that's taken from a paper from Liggett and Spitzer. This alpha is a localization function. So let's assume that it's one only at the origin, and it's measuring some sort of distance with respect to the origin. Points that are very far away have very little importance, and changes there are also going to be discounted by this factor alpha x. So typically we think of alpha x as e to the minus alpha absolute value of x. So that's a nice localization function for finite range transition kernels. The point is that there's an art in choosing these localization functions. They have to satisfy a certain compatibility with the diffusion kernel. Basically, what this is saying is that particles from very far away will not jump with very high probability to the origin. So let's say this is the origin. We're not jumping from very far away to the origin. So let me call this x. The origin here will be the y. And alpha of y is 1. So we're bounding the value that we jump from very far away to the origin. So that's the setup that Liggett and Spitzer set or decide to work. And then what they do is that they focus on Lipschitz functions and show that this is a semi-group on the space of Lipschitz functions, local Lipschitz functions. And then this is a rich set to determine measures they are able to complete their construction. But in our case, we're dealing with reactions that are nonlinear, and that breaks the Lipschitz property of our action. So we are not exactly in that set anymore, so we cannot use their approach. But there is a way out, and is a super martingale estimate. So the construction is based on what we call a Lyapunov function. It's not to determine recurrence or transience, but is just a function that examines the total mass of the system, or the distance between the evolution of these alpha norms. Basically, what we're going to show is that the distance between two processes that we have coupled, the infinitesimal evolution, is bounded by c plus 1 times the initial by the norm at the time. So this is the alpha norm. I forget always to say because there are many norms. Let me put here. Whenever there is a norm, is an alpha norm. Okay. So the way to get the super martingale estimate is to compensate, is to take a function that depends on time and on the configurations, which is compensating in time the rate of increase in the norm that's coming from the diffusion. So this is, in essence, our Lyapunov function. This we can show it satisfies a super martingale bound. So the total derivative dt plus L of this function f is negative, and this is what somehow Hugo asked in the first exposition, how we can use these thinking formulas to get semi-martingales or Lyapunov functions. So here it is, and this will be very useful for our extension because it bounds the distance between different processes in terms of the initial condition. So for any fixed time horizon, we have a construction by monotonicity. The configurations, the flows converge to a certain limit flow here in the space E alpha, and we have defined, and we have by our construction, this is already a right continuous function with left limits in the space of Cadillac trajectories, and the norm that we're looking here is the alpha norm. So the construction is done. Now that we have constructed it, our goal is to examine the family of interacting particle systems. So let me just simply write this in terms of our generators. So when you see here the generator, you shouldn't expect that we are going to take an exponential. This is just the recipe for following what we just did, for following the construction of infinite spaces, the extension to compact sets, proper formulation of the semi-martingale bound, and then the extension to the space of finite alpha norm. But what we do is when we look at these generators, we see the transition rates for birth and death of particles. And let me just say that the key point here is still unspecified. These functions, these reaction functions, are not specified. We are allowing them to depend on n, but they have to satisfy those hypotheses, right? F minus is dominating F plus. The difference is decreasing, and whenever we reach zero, we stay there. The way of closing the equation, of fully determining the rates, is by looking into the macroscopic object that we're looking at. We are interested in the fluid limit. That is, remember the story about the different levels of precision. So we have different, let's say, instruments that measure lumps of mass with more and more precision, but the lumps of mass are referred to as eta n for the level n, but the total mass, which is the same as we change the instruments, the reality is the same. The total mass has to be compensated by the level. So we divide by n to have a representation of what's happening in the total mass process. So that's the scaling for our macroscopic object. And then we have the macroscopic constraints, which reflect the net change in mass and the typical fluctuation we observe in these processes. These are just given to us at the start, at the set out, because we were interested in those particular stochastic differential equations. So if you remember, inspired by the SDEs, we build our interacting particle systems. And the point of this construction is that we have a uniform convergence of these quantities over compact intervals. So that's the constraint that we have. There are several ways of building these functions. They are not unique, but essentially when they differ in a negligible way in the limit. So it's irrelevant for the examination of our convergence scheme. All right. After the construction of the family, the question is, can we show it's tight? So the proof of tightness is based on considering a localization of our evolution inside a ball. So this ball here, remember that the sum of alpha x was finite. This means that alpha x tends to 0 as x tends to infinity, or goes away from any compact set of our vertex set V. So this is telling us that there are only finitely many. This is a finite set. There are only finitely many points that have a large alpha, and that's what we're calling here the alpha balls. They form a natural exhaustion of our vertex set. And based on that, we restrict our initial conditions here to have only particles inside the ball. Whatever particle was outside, we annihilate, and we don't look at the configuration with that particle. We remove it and now allow the system to evolve. So the truncation of the initial condition then leads to a series of questions as to how stable it is, how close it remains to the original one. And thanks to the super martingale estimate we had, the distance will basically depend on the distance at the initial time, and that's very small, because at time 0, the two configurations were converging to one another as we allow R to go to infinity. So we get this from the semi-martingale bound, the super martingale estimate. Let me write super martingale. bound. Well, it's going to go away in the next one, so I'm not right. The next condition is the condition that the particles that we started from, that started in a small or in a certain fixed ball, will not get very far away. So they essentially die out before or they never go very far in the alpha norm, right? So the way that we bound this is by looking at the evolution of the total mass of the system, which is not the same as the alpha norm. So it's not using the semi-martingale bound that we had before, but we're using the bound that we have on the total mass, and that's coming from the fact that the total that the annihilation dominates the creation of particles, right? So these two conditions allows us to concentrate on the oscillation of individual particles at a certain fixed site. So if we can control now the oscillations on a single site, and we can control then the oscillations on any finite box, since whatever is outside of the box is not really so important, we can control the oscillation of the entire process. And that gives us the second and the hard part of all those tightness criteria. The first one we can get just by applying from a straight, starting from our semi-martingale or super-martingale bound. So that gives us the tightness of the process. And what we turn to then is to examine the martingale problem, or where are the martingales converging to, the martingales associated to our process. So let me just remind you that for any function that is local and continuous, these formulas here are indeed Dynking martingales, are indeed martingales. We call them Dynking martingales because they resemble very much the ones that are constructed from actual generators. So this is just a formula that one needs to prove separately that it is a martingale indeed. Right. In particular, bounded continuous local functions, these two projections and the product of the projections, there shouldn't be an L here, sorry. These are allowed. So we can consider, let me remove this again. So we can consider the single coordinate projection and the product of two coordinates. These two martingales, they will tell us the expected value, what's happening with the drift and what is happening with the variance of our process. So let me just remind you or state what is the martingale problem. So we're given a differential operator. This A also may depend on eta. We're given a second order differential operator, and if we have a probability measure on, this is a finite dimensional statement of the martingale problem. So if we have a probability measure on this space for which these formulas here are continuous local martingales for every C2 function, then that's the solution to our martingale problem. Right. The point is that if we examine the test functions that are the basic coordinate and product of two coordinates, we can discover the quadratic variation of the martingales. That's the key idea. So as we're moving on, we are going to work on an infinite setting, and we cannot apply the d-dimensional result because we are in an infinite dimensional setting. But if we show that our family of martingales are actually represented by a Gaussian family, then we have essentially proved by hand all the requirements that we had to apply the formulation of the martingale problem. I'm just recapitulating. This is taken from chapter 5 in the book of Karatzes. I'm going just to write this here because I didn't. Karatzes. I think it's Brownian motion in stochastic process. I'm not entirely sure of the title. But anyway, in our case, the coefficients are this is the diffusion. The reaction and the diffusion, they appear in the drift. This is the reaction and the diffusion. And this is the noisy term here. I'm going to call it the variance. So that's our second order differential operator. And we have chosen our approximation scheme in such a way that we have a uniform convergence in compact sets for any of these test functions. So basically what we do is that we look at what's happening to these martingales. We know they're tight. We extract the convergent subsequence. We know what's happening for a convergent subsequence. The projections in a site assure us that we are living in a bounded region and the uniform convergence applies. The same thing we do for the product of the functions that look at the product of two coordinates. We are trying to get the correlations. The reason, if you compare here I've written explicitly the drift. Here I have left implicit the formula for L star. And that's because if you take here a function that is fx times fy of zeta, then we'll have two terms here, right? The one that derivates in x still captures the fy, and the one that derivates in y still has the fx. So we have in total three terms, two here and one here. And it's a very big expression, wouldn't fit. But the point is that when we combine all these informations together, we can determine the value of the quadratic variation of these processes. Right. And now we are going to build the Gaussian family, which is the step in the construction of the martingale representation of our projections. So take any projection, we can show that each coordinate that we have here is actually the stochastic integral with these variance scaling. So we construct underlying Brownian motions and represent our martingales in terms of them. And this means that we have obtained the integral solution to our SDE. So at this point, we would stop altogether and say, well, I have finished the problem because I have characterized the limit. Not quite. You have proven that the limit is a solution to this stochastic differential equation, but you don't know this stochastic differential equation has a unique solution, or you have to ask an analyst to explain you this. Usually that's what we do. We get to this point and we say, well, go to the analysis department and say, is this equation well posed or isn't it? So when we know it's unique, then is the end of the story. When that doesn't happen, you need to find another way of showing uniqueness, maybe showing that there is a uniqueness in a certain space, making sense of the solution that you're looking at. In our case, we got lucky because the super martingale bounds we had allowed us to say more than just how the terms in our sequence individually are built. They allow us to compare different initial conditions throughout. So we can make sense and show that, I'm just saying here that we found a solution. But what we can do is we can make sense using this uniform super martingale bounds. We can make sense of the distance between processes with different initial conditions. The same dynamics, different initial conditions. So we know from the first part, well, we didn't talk about this today, but we know that finite configurations do converge in the limit. And now we also know that they are uniformly close, so we can make a 3 epsilon argument to show that the different solutions are also close to one another. And that's showing us the property of the Cauchy sequence of our full initial problem. Actually, I'm not sure this is quite correct here because I have changed the M. But we can extend this 3 epsilon argument to these processes. Oh yeah, So these here, we use the semi-martingale, the super martingale bound. We use here, we use in the horizontal, and here we use the convergence. That's just the convergence. This is going to S star of R. So we can make the 3 epsilon argument across. So we can say that the processes themselves, they form a Cauchy sequence. And that concludes what I wanted to tell you about for now, for this first part. Thank you so much.
Thank you, Conrado, for the talk. Is there any questions? Yes.
Hello, can you hear me?
Yes.
Yes, go ahead, please.
Yeah, so are there like special cases of your SD which correspond to some kind of models that are already of interest?
Yes, good question. There is one case when we take, let me go back. When we take the kernel P to be nearest neighbor, let me see. Yeah. So when we take this to be nearest neighbor, so the discrete Laplacian on the graph, and when we take k to be 0, we can kind of remove this term. Actually, we have the freedom of doing that, and we take L equals 2. This is the parabolic Anderson model. You might be familiar.
Okay. Yes. Yeah,
right.
Okay.
So one of the motivations was to study stochastic partial differential equations, and moving to the infinite case is like a step in this direction. The interest is really to address these problems in the continuous setup. So there are that's part of the goal.
Okay, great. Thank you. Thanks very much.
Thank you.